So I click on summary, bracket Anova. I can highlight it, I can run it here as I mentioned before, or you can just hit enter and control and enter on your keyboard. So let's run it here. Okay, here is the results. The first thing that we should look at is probability. It's statistically significant, meaning that there is a statistically significant difference across the three SES groups in terms of their grades, which is the dependent variable. The three asterisks, as I mentioned before, indicates that the p-value is close to 0. There's another thing that we need to look at here, and that is the sum of square, sum SQ. Sum of square of especially residuals. So it's the amount of variation that's attributed to residuals or errors. That's, in other words, it's the amount of variance that is not explained by SES2 in the data. The amount of variation or variance that is explained by the independent variable SES2 is 334.8, and it's less than the amount of residuals. What we should do in statistical modeling is to aim for decreasing the amount of variation or sum of square, the amount of variation that is explained by residuals. So we're going to run another analysis and then another analysis to make sure that we will decrease the variation in residuals. So hopefully in our second analysis, the sum of square will be smaller. But we can test whether it is smaller or not. So let's go to the two-way Anova test. And I'm going to create this object as I mentioned before. In this analysis, we've got grade, tilde, SES plus gender. Tilde represents regression. So in a sense, Anova is really a regression analysis. We're asking R to regress grade statistically on SES2 and gender2 using this data set. And we can just run this. The object was created here at the bottom, as you can see on the right hand side, and I'm going to get the summary and quickly look at the p-values. Gender doesn't reach statistical significance, so it doesn't have any statistically significant impact on grades, but SES remains significant. And the interesting thing is that there is a slight decrease in the amount of sum square residuals, which is 624. Previously it was 631.1. This is not bad. So even though gender is not a significant predictor of grades, it contributes to the shrinkage of sum of squares and residuals, which is not bad. So I'm going to keep it in the analysis and run a third analysis, including the third independent variable, which is first language. So just like before, grade is going to be regressed statistically on SES, on gender, and first language this time around, this and the additional variable using the data set Anova. Let me hit Control and Enter, and the object is created three-way on the right hand side, and then Control Enter, and I'll get the summary. Very interestingly, we have got a statistically significant p-value, and this time round the p-value is has got two asterisks, which signify this part. You know, we can report that the p-value was smaller than 0.001, or you can just write the p-value equals this amount, 0.00872. The next thing we need to look at is the amount of residuals, where the residuals has significantly gone down from 624 in the two-way Anova to 602.1 in this three-way Anova, which is not bad news. So as we add more variables, we see that the amount of unexplained variance, which is attributed to error, is shrinking. Pretty good news for us. The next thing I want to do is to include an interaction. And what do you mean by interaction? You see, grade is regressed on SES, gender, and first language, so that's good. It's pretty much like the previous analysis. But plus the interaction between gender and first language. Now, this interaction term is created in this way. There has to be an asterisk between the name of the two of the independent variables in the analysis. So the independent variable has to be among these three. Then you can change this. For example, you can change SES2 times gender2, or I don't know, SES2 times first language, etc. So let's run this analysis. Feel free to add on more interaction terms and test more models. Run it. I just ran it, and interaction has been created on the right hand side for me. Summary. Very nice. The first thing that catches my eyes is that the gender first language is a statistical significance interaction. So the variation in the data is not only explained by main effects, SES and first language, not by gender really, because it's not statistically significant, but also by interaction effects, which is gender by first language. So you need to keep this in mind. In the previous videos, I have explained how to justify this and how to write the report and what that means exactly for your analysis. But the very interesting thing that I observe here is the fact that sum of square residuals has decreased quite significantly from 602 to 563.5, which in my opinion is excellent. So as we included more and more variables, the amount of variation in residuals decreased. So far so good. Now we have got 4 models here. Yes, just by looking at residuals, you may say that the last model was the best. But the point is, we need to make a decision by looking at the global fit statistics. They are going to be generated by using this tool. So you need to include library in brackets AICwt mod AVG. Just copy and paste it in exactly the same way to prevent receiving error messages, and open the library. So after this, we will run this code. The first code that we have to run will generate what is called a model set. And the second code we will run is going to generate a model names. So 2 objects will be created for us. Model set is created in this way. We just want to list all the models, all the objects that we created earlier. Do you remember those names? And we just want to run a new object has been created. See, model set on the right hand side. And the model names, we want to concatenate the one-way test, the two-way test, the three-way test, and interaction test. All of them have to be put in double quotation marks. So let's run this. Control Enter, and another object has been created on this side for us. And finally, we want to run the AIC test and BIC test. For AIC test, just include AIC tab, then model set. You see, this is the model set I created. Then mod names equals mod names and sort true. When you choose sort true, they're going to be sorted from the smallest to the largest. So let's run the first analysis and go through the results. The results are here. As I have discussed in quite a few other videos before, AICs indicate a global fit, and the smaller they are, the better the fit of the model to the data set. In this case, I have the interaction test, which is 783.58 in terms of its AIC statistic. And it is smaller than the rest of AIC, so this is the first indication that the best model is the interaction model. It is also in line with the amount of residual, sum of square residuals, which I displayed before. Another indication is this AIC weight, or the weight of AIC. The weight altogether of this AIC weight of all of these models should add up to 1 because they're normalized. So it beautifully adds up to 1. The first one is perfect 1 and the rest are 0. Now, if any of these AIC weights is smaller than 0.01 or smaller than 0.05, just like the alpha value that you consider for your statistical analysis, then that model can be safely neglected. Actually, these three models are, just 0. So they're obviously smaller than 0.05. So these three models can be neglected. This is another indication that the best model is the interaction model. And finally, LL, or log likelihood statistic, is interpreted in the same way that AIC is interpreted, meaning that the smaller LL, the better the model. So again, this is smaller as 0.384. I mean, that's the absolute value of it is smaller than the absolute value of the rest of them. So it's another piece of evidence for us that the best model is the interaction model. And finally, we can run the BIC tab. It's exactly the same format as the previous one. And here we will get the BIC statistics. Again, they have been organized from the smallest to the largest. And as you see, the smallest continues to be the BIC of the interaction model, which is 806.01, quite smaller than the rest of them. And the BIC weight is telling us the same story because, first of all, if you add these up, they're almost 1. I mean, we have only 2 decimals. That's why they don't completely add up to 1. They add up to 0.99. But if we had 3 decimals or 4, they would have added up to perfect 1. But at the same time, we see that the interaction model's BIC weight is pretty close to 1 and is 0.94, and the rest of them are smaller than 0.05. This is another clear indication that the best model is interaction, and in the same way, the LL, or log likelihood statistic, is also smaller than the rest of them. Its absolute value is smaller than the rest of them. So now we know that the best model among them is our interaction model, including those 3 variables plus 1 interaction term. And now we want to figure out the effect sizes of the independent variables and the interaction terms. So let's do that. First of all, we have to call the library effect size. So let me do that. Okay, so the library has been called. It's a warning message, not a big deal. I can generate eta squared first. So partial true. So this will give me partial eta squared. If you don't want the partial version of eta squared, you can just change this into false. But I want that, so I'm going to click Control and Enter, and this table beautifully represents the partial eta squares for me. As you can see, the SES2 has got the highest partial eta squared value with a confidence interval between 0.8 to 1, 95%. Gender has got a very small one. Since this is not a significant predictor, so we can just ignore this. But for first language, we have a small amount of effect from first language and a small amount of effect from the interaction term. Altogether, these 3 effect sizes range from pretty small to pretty large for SES. Again, in previous videos, I have discussed how to interpret eta squares, but anything around 0.1 is small, and so on. I will just present a slide in a second to show you how you can interpret omega and epsilon as well. So let's run the omega squared analysis, and we will get more or less the same sorts of eta squared, and it clearly indicates that SES remains to be the most powerful predictor of grades, with the rest of them, the rest of the independent variables being a weak predictor. They are still significant, but they are weak predictors. And for epsilon squared, we have the same story, so it's exactly the same as partial eta squared. Now, in some analysis that you may run in the future, you may find out that these statistics are not exactly the same. So how you can interpret it is in this way. Epsilon squared is, as I mentioned, is a measure of effect size. You can read the original paper by Kelly in 1935. Now, according to Friedman et al., 2017, epsilon squared is just the adjusted R squared value, which is reported in many data analysis programs. And adjusted R squared is R squared adjusted for the sample size. In the same way, omega squared value is a measure of effect size, or the degree of association of a population, and ranges between -1 and +1. It simply indicates how much in percentage of the variance the dependent variable is explained by the IV in the analysis. And if you want to interpret them in a different, based on some criteria, this is the criteria that you use. And I think I just made a mistake. I think I said 0.1 is small, but I need to correct myself. This 0.01 is small, 0.06 is medium, and 0.14 is large. So in this scenario, basically this is large, this is medium, and this should not be interpreted because it's really not statistically significant, so we don't interpret that. Okay, the last thing we want to do is post-hoc analysis. There are many different types of post-hoc analysis. You can run the Toki without opening any library, but I leave this code for you. You can just run it on your own. What I would like to show you is that using this cool library called Desk Tools, you can run all sorts of post-hoc analyses. So let's open it first. Okay, it's opened. Good. There's a warning message, which is okay. Now, the first analysis that I want to run is HSD. That's a type of post-hoc analysis. Other types of post-hoc analysis are displayed here. HSD, bonferroni, LSD, scheffe or scheffe, newmankeuls, and duncan. Now, the first analysis I want to run is HSD for you, and this is the code: post-hoc test with P and H and T being capital letters, and then interaction, comma, which equals null, method C HSD. C stands for concatenation. And then the confidence interval is 0.95. If you like, you can change it to 0.99. That will be a very stringent confidence interval that's used in some research studies. And if you want to order them, you can change false to true. It doesn't really make a big difference. It's just the organization will be probably more appealing to many people. So let's hit Control and Enter, and HSD again, Control and Enter, and the results are here. There are actually many results starting from here. First of all, in SS2 or socioeconomic status values, low and high groups have been compared in their grades, and what we see is the p-values of a very small p-value, which is statistically significant. The rest of the analyses are also in the same way statistically significant. For example, mid versus high and mid versus low. In this case, the differences should also be consulted with. You look at the differences between the high and low group in their grades, and you see it's negative, so it's in favor of low, meaning that the low group had a high score. The other way around. It's negative, so it means that the scores were in favor of the high, the second group. And the same way, the high group had a higher, on average, higher score than the mid group, and the average difference between them is minus 1.92. And similarly, the difference between mid and low is significant, and mid group has on average 1.314286 grades higher, is that much higher than the lower group. The gender differences are not statistically significant. It's not surprising because we saw this before. The differences between first language and second language is significant, as you see, and it's in favor of English speakers rather than non-English speakers. So finally, if you look at the differences between males English, and this is the interaction one, male English versus female English, it's statistically significant. The other one, the second one, is also the same, and the third one is also the same. So out of 6 interaction comparisons, 3 of them are statistically significant. Now we can display these beautifully in a plot, which is generated by use of this very brief text or code, if you will. You just write plot bracket HSD comma by LAS equals 2, and that's LAS stands for labels of the data on the horizontal axis. So let's run this, Control Enter, and in a second we're gonna have, yes, this is the label. I should here, I mean here you can see it better here. It's very clear that the first analysis on top, which are represented by these whiskers, are not crossing the 0 line. If any of these whiskers crosses 0 line, well, it indicates that they're not statistically significant. The whiskers represent those 95 confidence intervals. You can see the same thing in the output as well. If 0 falls between the lower confidence interval and the upper confidence interval, then that relationship is not statistically significant, which is not the case because 0 does not fall between these two. But if you go further down here, you see lower confidence interval is minus 1.82 something, and the upper one is 0.21 something. So this indicates that 0 falls somewhere between this interval, and as a result the p-value is not statistically significant. And the same applies to this and to the last, and this is the visual representation. As you see, the confidence interval crosses the 0 line, and therefore these 3 are not statistically significant. This brings me to the end of this video, everybody. It's been a long one, so I'll probably have to cut it into 2 sections. By the way, if you heard a lot of clapping thunders in the background, I'm very sorry about that. If you like the video, please give it a like and subscribe to the channel. I will soon make another video about Anova and other multivariate analyses. Have a good day.